at the Claisen condensation of an ester to a beta keto ester. And what you would need to have to begin with is an ester, of course. And in addition to the ester, you need to have a base so that you can remove a proton on the alpha carbon. Now, when you look at most textbooks, they're going to use an alkoxide as the base of choice. When you use an alkoxide, the conjugate acid of that alkoxide is an alcohol, which has a pKa around 16. But these protons on the alpha carbon here that I'm drawing in green have pKa's in the mid-20s. So that reaction actually favors the reactant side significantly. If you want it to actually go and go well, you want to use a stronger base for that job. The best base for something like this would be LDA, which stands for lithium diisopropylamine, and then you would follow it up at the end with some acid. So these would be the conditions that would help this reaction go favorably. So I'm going to draw out the structure right here of LDA. So there is a lithium, it's a spectator ion, and then we have our diisopropylamide. And it is the conjugate base of an amine, and amines do again have pKa's around 36. So by doing this acid-base chemistry, you will be able to make a weaker acid-base pair, which is why you want to do it. So this base will be able to remove one of these alpha protons and give the electrons back to the alpha carbon. By doing so, you are going to make an enolate of an ester. I'm going to draw on that hydrogen that is still there so that you don't forget that it is there. And then we have our conjugate acid, which is our amine. It's a spectator at this point, but it is there. I don't want you thinking it disappeared somehow. But this particular enolate does have resonance delocalization of the negative charge. The hydrogen isn't going anywhere on that alpha carbon. Okay, so these are the two resonance structures of this enolate. The one on the top is the less predominant resonance structure, and the one on the bottom is the more predominant resonance structure. But I find that when I do mechanisms, it's easier for me to use the one on the top, since it is the carbon that bears the partial negative charge that is actually going to add in the second step. So for me, that one is easier to use. But you can use either of these. It doesn't really matter. Now, this is going to be a weaker base than what you started with, based on the conditions we are using. And this particular base, which has resonance stabilization of its negative charge, will now react with another ester in solution. It will act as a nucleophile. And so, you can show this from either resonance structure, but the alpha carbon will add to the carbonyl carbon and you will break the pi bond. For me, this is easier to see. If you want to use the other resonance structure, you can. You'd need to reform the pi bond between the carbon and oxygen, and then use the electrons in this double bond as the nucleophilic electrons that are adding to that carbonyl carbon. You can do this from either resonance structure. And you will make an anionic form of a tetrahedral intermediate by doing so. And I'm going to draw out the pieces and parts so that we can see what has gone where. Okay, so this is the intermediate that you're going to get. I'm going to color code the different pieces and parts so you can see what came from where. This part here in blue, it comes from the enolate part, and you can do that again from either one of these two resonance structures, but that's what part we're talking about. And then this top part here, this came from the ester that was attacked. So that's which part ends up where as you look at this intermediate here. Now, there is a tetrahedral carbon up there on the top, and you're going to want to reform the pi bond. Now, unlike an aldehyde or a ketone in the aldol condensation, we do have a decent leaving group here because this was an ester. So we can have the carbon-oxygen bond reform that double bond, and we can kick out an alkoxide leaving group. In this case, that would be a methoxide. But you could do this because by doing so, you're going to create a weaker base than LDA. And if you are using an alkoxide in the beginning, you're not making a stronger base by doing so. So you do have a decent enough leaving group for this to occur. And it will go. When this has occurred, I'm going to try to leave things in similar locations so you can see what ends up where. We're going to make the beta keto ester, but it's not stable at this point in time, even though we actually have formed it. Now, the reason this is not stable is because it is a beta keto ester. And you have an alpha carbon that is alpha to both the ketone component and the ester component. And its alpha proton has a pKa around 11-ish. And this base here, the alkoxide base, is a strong enough base to remove this proton. And it will do so. So you're going to have the base come in here and remove the proton, and you will give this pair of electrons back to the carbon, creating another enolate that has resonance stabilization of its negative charge. So I'm going to try and do this on the next page. So you've got a methanol, remember that. I'm just not going to draw it on this page because there is not going to be enough room for that. Okay, so here is one of the three resonance structures. This negative charge can be delocalized onto the neighboring groups. So I'm going to show it delocalizing onto the ketones oxygen first. You could also delocalize it onto the esters oxygen. I'm going to try and squish that in down here. Don't have enough room to draw the lone pairs on that oxygen, but there would be lone pairs on there. Okay, so these are the 3 resonance structures we would have. Now notice the one that I squished there on the bottom and the one over there on the right do contain conjugated pi systems. So this is why that proton back here in green was acidic. When it is removed, you get 3 resonance structures showing the delocalization of this negative charge. And 2 of them have conjugated pi systems. So it's highly stabilized by doing so. Now, this is where it's going to stay in solution, and you would also have the methanol present at this point. And it has nowhere else to go. This is the end of step 1. It's step 2 that we actually reprotonate this enolate. So in step 2, we would add the proton from an acid source. And I'm going to redraw my favorite of those 3 resonance structures so we can use that one. But again, you can use any one of them you want to show the protonation, but either way you're going to protonate the carbon that is alpha to both of the carbonyl groups. Okay, so you add the acid source. Doesn't really matter what your acid source is. And your enolate will pick up the proton and give electrons back to the oxygen, so that at the end of the day, you make the beta keto ester. This is how it's done, and the reason we call it a beta keto ester is because the ketone group is in a position beta to the ester's carbonyl carbon. So these 2 carbonyl groups are beta to each other. One of them is a ketone, one of them is an ester, and that's why we call it a beta keto ester.